Hi everyone. Welcome to our lecture video on section 1.7, where we're going to be learning some basic concepts of probability. Let's start at the bottom of page 1 with some definitions. First of all, a probability experiment is an action or trial through which specific results, whether they be counts, measurements, responses, are obtained. An outcome is the result of a single trial in a probability experiment. The sample space is the set of all possible outcomes of a probability experiment, and an event consists of one or more outcomes and is a subset of the sample space. I'm going to show you all of these definitions with some particular examples. So if you go to the top of page 2, I'm going to outline each of those definitions with a nice, simple scenario. First of all, the probability experiment here is going to roll a single die. So not even a pair of dice, just a single die that we're going to roll here. Now an outcome is any particular result of that experiment. So for an example, an outcome of this experiment listed as a set might be rolling a 3. The sample space is the set of all possible outcomes. In this case, all possible outcomes are 1, 2, 3, 4, 5, or 6. Those are all the possible outcomes when we're rolling a die. Finally, an event is some sort of subset of that sample space. Perhaps we're interested in the event of roll an even number. And we could describe the event in words like I've done here, or you could actually list out the outcomes. In this case, rolling an even number would consist of the outcomes 2, 4, and 6. So again, the experiment is rolling a die. Outcome is any particular result. Sample space are all possible results. And an event is just some subset of that sample space. Now, if you look at the bottom of page 2, they put this into the context of identifying a sample space for a probability experiment. For instance here, a probability experiment consists of tossing a coin and then rolling a 6-sided die. We want to describe the sample space. Now when they talk about describing a sample space, essentially here what we're going to do is list all of the possible outcomes. So I'm going to call this set S for sample space. And I'm just going to go through the different possible scenarios that we could encounter. So if we toss a coin, one outcome for that coin is to land heads up. And then I roll a 6-sided die, so perhaps I toss a heads on that coin, and then I roll a 1 on the die. Now, of course, that's just one outcome. Another outcome would be H2, H3, H4, etc. So here's H5, here's H6. One thing you can always do when you're listing a sample space, you don't have to necessarily show every possible outcome. So while I've done that for all of the H or the heads, I'm now going to do the tails in an abbreviated format. So this would be T1, and then I'm just going to use an ellipsis here all the way up through T6. So we can identify here that there are 12 outcomes total. So even if we don't list every single one of these, what's important to understand is the total number of outcomes. For the next definition, I'm going to go to page 3, and they talk about what are called simple events in probability. A simple event is an event that consists of a single outcome only. For an example, if you toss heads and roll a 3, that outcome is H3. That's a simple event. If an event that consists of more than one outcome, that's not a simple event. So if I said something like tossing heads and rolling an even number, well, there's more than one outcome that satisfies those conditions. So that's not considered a simple event. Down at the bottom of page 3, they give us a scenario. They tell us to determine whether this event is simple or not. You roll a 6-sided die. Event B is rolling at least a 4. So if you actually look at those outcomes, and I'm going to label this set B, event B, The outcomes that qualify for this definition, event B is rolling at least a 4. Your outcomes would be 4, 5, or 6. Since this event contains more than one possible outcome, it is not a simple event. Again, simple events are nice because they have one outcome only. Other times, events might contain a large number of outcomes, and the sample space itself could be very large. Like I said earlier, sometimes what's important is not necessarily to be able to list all of those outcomes, but merely to count them. We need to know how many of those outcomes exist. One of the ways we're going to do that is outlined on the top of page 4. This is called the fundamental counting principle. If one event can occur in A ways, and a second event can occur in B ways, then the number of ways the two events can occur in sequence is found by multiplying A times B. Now, of course, this definition can be extended for any number of events occurring in sequence. So it doesn't mean you just have two events going on. You might have A times B times C times D, etc. And that would just continue for every event in the scenario. I often refer to this fundamental counting principle as what I call the slot method. Because basically what you do here is draw out a slot for every decision or choice or option that you have to make. I'll show you what I mean by looking at the example at the bottom of page 4. Here it tells us that we're purchasing a new car. The possible manufacturers, car sizes, and colors are listed here. So the manufacturer we're going to choose is either Ford, GM, or Honda. The car size is either compact or midsize. And the colors that we're finding acceptable are white, red, black, or green. What we want to know is how many different ways can you select one manufacturer, one car size, and one color. I'm going to show you how to get that solution using that slot method, that fundamental counting principle. We can also use what's called a tree diagram to check that result. So the way a slot method works, let me move this up just a little bit here, make sure I have plenty of room, is I'm going to draw out a slot for every choice or decision that has to be made. And I'll often label these slots so it helps me keep track of what I'm doing. So here the first choice that we have to make is we have to select a manufacturer. Next, we need to select the size. And finally, we need to select the color. Now, these don't actually have to be done in this particular order, but when you fill in the number of options for the manufacturer, we have 3 options. For the size, there's 2 options. And for the color, there's 4 options. The fundamental counting principle, or slot method, tells us now to just multiply those options together, giving us a total of 24 different scenarios. So how many ways could we choose that manufacturer, car size, and color? There's 24 different possible outcomes. Now you can see this visually using what's called a tree diagram. Basically the way that works, and I'm going to start right here, I put this point, and this point represents a choice. The first choice we're going to make is the manufacturer. So this tree branches in 3 directions. Right? We've got 3 different manufacturers from which to choose. And you can label this. This would be the manufacturer Ford, GM, or Honda. Now once you choose that pathway, you then have to choose the car size. And that car size would be compact or mid-size. I'm going to label those as C or M. Now even if we had selected the GM, we would still have the same number of options for that next choice. We could choose a compact or a mid-size. Likewise for the Honda. If we decided to go that route, we would then choose between a compact and a mid-size. So compact or mid-size. The last choice that we have to make is the color. And regardless of the path you're on, you have 4 options for the color. So for instance, if you choose a Ford Compact, you now have 1, 2, 3, 4 options for the color scheme at the end. Ford midsize, same thing. There's 1, 2, 3, 4 color choices. Likewise for every remaining branch. And the idea here, and I'm not going to label those because I don't want the picture to get too cluttered, but the idea is that when this picture, this graph is complete, you can literally count the number of pathways. And all you have to do to count the number of pathways is count the number of terminal points, which in this case I've got 6 groups of 4, or 24 different pathways. The tree diagram is fine. It's more of just a visual interpretation of what that slot method has already shown us. Now, as far as probability itself goes, we're going to turn over to page 5 and explore the different types of probability that we want to be familiar with. The first, and maybe the most important, is what is called classical or theoretical probability. This is where each outcome in a sample space is equally likely. To calculate the probability of some event E, we simply take the number of outcomes in that event and divide by the number of outcomes in the sample space. That's going to give us our probability. And our probability will always be listed as a fraction, or a decimal, or a percentage. Now, one thing I'll add on to this, and it's really okay whichever of these formats you choose, if you go the fraction route, we always want to make sure that that fraction is completely reduced. Now, you'll see when you're doing your MyStatLab assignment, sometimes they'll ask for the answer as a fraction, other times as a decimal or a percentage. So just make sure, if it's not specified, you could choose any of these formats. It's really up to you, but make sure you're looking on MyStatLab because usually they'll specify how to format your answer. If you look at the bottom of page 5, they've got an example where we're told that we roll a 6-sided die. We then need to find the probability of each event. So the first thing I'm going to do before I look at any of these particular events, I'm going to list out the sample space. And it's a simple sample space. I'm going to list it up here as set S. And remember, rolling a 6-sided die, there's 6 outcomes. 1, 2, 3, 4, 5, and 6. So there's 6 outcomes in our sample space. For event A, we want to know the probability of rolling a 3. So I'm going to go ahead and list the answers down below. The probability of event A. Notice the notation here, probability, and then in parentheses, you either list or describe the event. Probability of event A. Well, there's only one outcome that's a 3. And so there's one successful outcome out of 6 outcomes total. So that probability is 1/6. For the second one, event B says, what's the probability of rolling a 7? Well, notice that's not possible given this sample space. The number only goes up as high as 6. Now, anytime you're asked for a probability for an event that's impossible, there's still a probability. It's just always 0. So make sure you realize in probability, there's no such thing as a trick question. If they ask you something that cannot possibly happen, the probability is simply 0. On to the next one, event C. The probability for event C, rolling a number less than 5. If you look at your sample space, there's 1, 2, 3, 4 numbers that are less than 5. So that probability is 4 out of 6 total outcomes. Of course, if I leave that as a fraction, I just need to reduce that to 2/3. And then finally here for event D, probability of event D, rolling a number greater than 0. Well, notice all of the numbers in the sample space are greater than 0. So this is an event that's guaranteed to happen. That means its probability is 1 or 100%. So again, probability is what you're noticing here, or 0 for something that's impossible, 1 for something that's guaranteed, and it's a proper fraction for anything in between. If you turn over to page 6, we'll look at the next type of probability. This is what's called empirical or statistical probability. This is another one we'll be seeing quite a bit in this course. This is when we make probabilities based on observations obtained from probability experiments. Basically, you're using past data to indicate future probabilities. Another way to think of this, it's a relative frequency of an event. So the probability of event E is the frequency of event E divided by the total frequency. In shorthand, that's F over N. Your formats would still be the same. It's either a reduced fraction or a decimal or as a percentage. If you look at the example down below, bottom of page 6, it tells us here that a company is conducting a telephone survey of randomly selected individuals to get their overall impressions of the past decade. So anything in the 2010s. So far, 1,504 people have been surveyed. What's the probability that the next person surveyed has a positive overall impression of the 2010s? So again, this probability here, and I'm going to write it in that shorthand, the probability, and you can, shorthand this. You don't have to write out a complete sentence, but I want the probability of a positive overall impression. What I'm going to do is look at this past data in order to predict future probability. So in this case, there were 406 respondents who felt positive about the past decade, and there were 1,504 respondents total. Now, with something like this, it's not a nice, easy fraction. I would most likely express this as a decimal. So I'm just going to type that into the calculator here, and that's 406. Let me get that 0 in there, 406, and I want to divide that by 1,504. So as a decimal, that's 0.2699, etc. I'm going to round that to 2 decimal places. So this is approximately 0.27, or about 27%. Remember, if they don't specify the format, you're welcome to use any of the 3. If they do specify a format, just make sure you're following, reducing your fractions, and of course rounding your decimals appropriately. If they don't specify the rounding, just make sure to show at least 2. Now, one thing that's important to understand with empirical probability is a concept called the law of large numbers. What this tells us is that as an experiment is repeated over and over, the empirical probability of an event will approach the theoretical or actual probability of the event. And a classic example of this is simply using the probability of tossing a head. If you're tossing a coin, what's the probability of tossing heads? Well, we know theoretically that should be 50%, right? Half the coin tosses should be heads, half those coin tosses should be tails. Now, of course, that doesn't guarantee anything in the short term. For instance, if I toss a coin 10 times, there's no guarantee I'm going to end up with exactly 5 heads and 5 coins. In fact, when you look at the number of tosses for the short term, like right here, that's about 20 tosses, you could kind of be all over the place. Maybe right at the beginning, you have a lot of heads that are being tossed. After that, you have a lot of tails that are being tossed. As the number of tosses continues to increase, those results will eventually balance out to exactly 50%. Again, that's what's called the law of large numbers. Anything can happen in the short term, but in the long term, those probabilities will distribute exactly as they should. The last type of probability, as indicated at the bottom of page 7, is what is called subjective probability. Now, we don't really see this a whole lot in the course. This type of probability is based on an intuition or educated guesses or estimates. For example, a doctor may feel a patient has a 90% chance of a full recovery. That's an expert opinion. Another good example would be weather forecasts. You can watch 3 different channels for the weather forecasts, and each of those experts are going to make different predictions. One might say there's a 70% chance of rain tomorrow, while the other channel says there's an 80% chance. Those are experts that are looking at the same data and making different opinions or different conclusions based on that data. That's subjective probability. In fact, if you turn the page over, we'll take a look at some scenarios. And they're just asking us here to classify each of these statements as an example of classical, empirical, or subjective probability. So the first statement says the probability that you would get the flu this year is 0.1 or 10%. That's an example of subjective probability. That's an expert opinion. That's a medical opinion. It would be like any sort of medical prognosis where they say they feel the patient has a 95% chance of full recovery. You have a 10% chance of getting the flu this season. The flu changes from one year to the next. So that probability is subjective. It's based on expert opinions. The second scenario says the probability that a voter chosen at random will be younger than 35 years old is 0.3 or 30%. This is not subjective. This is not an expert opinion. We can make this type of probability simply by looking at past data. This is what's called empirical probability. When you look at past information, you can see how many voters turn out for each election. You can see what their ages are and so forth, and you can use that data to make future predictions. Finally, the probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. Well, this is a classical or theoretical probability. This is based on every ticket being equally likely to win. Equally likely outcomes is always indicative of classical or theoretical probability. Now, as far as that range of probabilities, we discussed this back in one of our examples. Just keep in mind that the probability of an event E is always between 0 and 1 inclusive. You can have a probability of 0. You can have a probability of 1. More mathematically stated, 0 is less than or equal to the probability of E, which is less than or equal to 1. And you can kind of see this little scale they've drawn out for us. Anything from impossible to certain, all the way right to the middle of being 50-50. There's just a couple more concepts that I want to share with you here. On page 9, they talk about what are called complementary events. It's kind of like a complementary angle. You know, complementary angles in geometry are two angles that together make up a right angle. So it's kind of like the leftover. The complement of an event E is the set of all outcomes in a sample space that are not included in event E itself. This is always denoted as E with a stress mark. We read this as E prime. So if you look at the illustration, suppose this rectangle represents our sample space, and in that sample space you have event E. Well, then E prime, its complement, is simply everything else, every other outcome that's in the sample space, but not part of event E. One important thing to notice here, when you look at any event and its complement, it accounts for the entire sample space. And we call this a law of total probability. I'm going to write it out here that if you take the probability of event E and you add the probability of event E prime, so this is the probability of the event plus the probability of its complement, that always adds up to 1. It has to. When you look at an event and its complement, you're always accounting for every possible outcome. If you look at the example at the bottom of page 9, it kind of shows us how we can use that concept to answer probability questions. So it tells us here that you survey a sample of 1,000 employees at a company and record the age of each. We want to find the probability of randomly choosing an employee who is not between 25 and 34 years old. Now notice what we want, the probability, and I'm just going to jot this down in shorthand, not between 25 and 34. That's what we want, okay? Now if you look, and I'm going to mark these on the chart, there's a lot of categories that make up that event, not between 25 and 34. So this first category would qualify. Let's see, this category here would qualify. The category here, here, and here. In fact, there's only one category that doesn't qualify, and that's the category right here. So instead of going through all of the different categories that satisfy the definition of the event, it's easier to calculate the probability of what we don't want. In this case, notice that probability of being between 25 and 34. It's a simple probability. It's 366 out of the total 1,000. Now notice that fraction, that probability, are for the outcomes that we don't want. To find the probability for all of the outcomes that we do want, we'll simply subtract that from 1. Remember, the law of total probability says an event and its complement always have to add up to 1. And now we've got a nice simple way to get our final answer. So I'm going to show you the calculation and we'll move on from there. So 1 minus 366 divided by 1,000. Notice our probability, our final answer is 0.634. So I'm going to go ahead and jot that down and we can move on from there. It's just sometimes easier, it's nicer to use a complement. That's a little bit easier way to get the overall probability that we're looking for. Moving on to page 10, there's just a couple last ideas I want to share with you here. In this example, it tells us that a probability experiment consists of tossing a coin and spinning the spinner that's shown. Now this may not be showing up great on the camera, but if you look at your handout, this spinner has evenly divided spaces numbered 1 through 8. So the spinner is equally likely to land on each of those numbers. They tell us here to use a tree diagram to find the probability of tossing a tail and spinning an odd number. So if you think about that tree diagram concept, I'm going to start here by tossing my coin. Now when I toss a coin, I can follow the heads path or I can follow the tails path. If we go the heads path, we then have 8 outcomes total when we spin that spinner. So I'm going to draw in 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to number those. So 1, 2, 3, 4, 5, 6, 7, and 8. And of course, had we tossed tails on the coin toss, we would still have 1, 2, 3, 4, 5, 6, 7, 8 outcomes for that spinner. And I'm going to label those as well. So notice, by drawing out that tree diagram, we can see there's a total of 16 outcomes. Now they're asking us to find the probability of tossing a tail and spinning an odd number. So now I'm going to circle all of the outcomes that satisfy the conditions of that event. So we have to toss tails here, so I'm down on this path, and spin an odd number. So I'm circling 1, 2, 3, 4 outcomes total. So this probability of tossing tails and spinning an odd number, there's 4 successful pathways out of 16 total. And of course that would reduce if you want it as a fraction, that's 1/4. If you prefer it as a decimal, that's 0.25. And if you want it as a percent, that's 25%. Remember, all of those formats are fine. Just make sure if you do it as a fraction that you reduce. The last example that I want to show you here is at the bottom of page 10. tells us that your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? So before we can do a probability, we have to know how many different ID numbers there are total. This is where that slot method comes in. You have a total of 8 digits in your ID number. So I'm going to draw out 1, 2, 3, 4, 5, 6, 7, 8 slots. Each one represents a digit in your ID number. Now it tells us that each digit can be anything from 0 through 9. So you have 10 options for that first number. That first digit in your ID can be anything 0 through 9. It also tells us that each digit can be repeated. So you have 10 choices every single time. Now, of course, the slot method tells us we have to multiply all of those outcomes together. And when we do that, you've got a total of 1, 2, 3, 4, 5, 6, 7, 8 zeros here. So that as a number, when I write that out, you can see there's a lot of different ID numbers. That number is 100 million. So there's 100 million different ID numbers based on their criteria. Now, what is the probability that we would randomly get your college ID number? So basically, your ID number, imagine if I was just trying to guess what your ID number is. Well, there's only one successful outcome out of 100 million total possibilities. So notice here the probability is extremely low, which of course we already knew, but here you actually see the results. 1 out of 100 million. That's the probability that I could just randomly guess your college ID number. All right, so that's just some basics for probability. Of course, we're going to expand on this over the next few sections, but for now, go ahead and try the assignment on MyStatLab. And as always, if you have any questions, make sure to let me know.